Dear ladies and gentlemen, it is a great pleasure for me to present our results here on the conference Nonlinear Dynamic and Complexity. First of all, we thank the organizing committee for the possibility to give us to present our results here, and also for organizing the conference. Our topic today is the evolution of thermal diffusion measurement by statistical mathematics. First, in an introduction, we gave a short overview and give the necessary definitions and formulate the so-called variance theorem. This theorem we apply to infinite boundaries and anomalous diffusion. In a third chapter, we use the variance theorem in order to compare theoretical and experimental. This fourth part is dedicated to the so-called Poznaniak experiment, which is a rod covered with thermocouples, and we use the variance theorem in order to determine parameters. A short conclusion summarizes our results. So heat diffusion is an important effect and belongs to complex systems where the ingredients, basic ingredients, are moving. These can be characterized by a large diversity of elementary units and strong interactions between these things. The automotive application of this heat diffusion is in constructional or functional materials exposed to high temperatures. Such kind of compounds are aluminum-based alloys for cylinder heads in combustion engines, stainless steel or nickel-based alloys in turbochargers, or FeNdB permanent magnets in electrical engines. In order to reduce the amount of experiments, the simulation of such complex system is coming into consideration. So now concerning heat diffusion, due to the famous works of Einstein and Smoluchowski, there is a connection between diffusion and statistical physics. In order to understand this and formulate it carefully, we need the following definitions. A distribution function f of t and x is called the fundamental solution of a Cauchy problem for the heat equation if it solves the following initial value problem. We have our diffusion equation, and for the initial condition, the Dirac delta function. The solution of this kind of problem, Cauchy problem, is similar to the Gauss distribution, which we can see here. If we compare this with the usual Gauss distribution from literature, we find that the expectation value mu is equal to 0, and the variance sigma square is equal to 2 dt, which is proportional to the time. That leads to a connection between heat diffusion and statistics. So we have seen that the statistical momenta became an important rule. And for this, it is necessary to define them, in this case, in finite boundaries. So let x be a continuous random variable with the related distribution function f of x in a special interval, a smaller than x smaller than b. Outside this interval, this function is 0. Then the E's momentum can be defined by the integral from a to b, which are the boundaries, and a potential function x to the power n multiplied by this distribution function. The E's central momentum is a little bit similar. It's also defined by a finite integral, but in this case, the variable x is, from this, it is subtracted the quantity m of 1 over m of 0, and this to the power m. So from this definition, which we have seen here, we can extract the expectation value by this rational figure, m of 1 over m of 0, and the variance is a little bit more difficult, can be expressed as you can see on the slide. So with these things at hand, we can formulate the so-called variance theorem. We know that if we consider a linear initial boundary value problem, the general solution can be represented as a Fourier Laplace convolution with initial values and with boundary conditions. So if we consider now the momenta of such kind of convolution, we see by applying the binomial theorem that the convolution splits into the momenta of each function f and g. Yes, and and from this we can follow for the expectation value of a convolution, it splits into the sum of expectation values. The variance of the convolution splits into the sum of variances of each part of the convolution. And for the asymmetry, we have got quite the same. So the next question is how we can realize such kind of things. So we know from the classical Brownian motion that the variance is proportional to the time. But in several experiments, deviation of such kind of behavior is observed, and these things can be collected by that the variance is proportional to a potential function of t, where the exponent is a rational number. So this leads to the fact that Metzler and Klafter started to classify diffusion processes. So if this parameter alpha, this exponent, is between 0 and 1, we are speaking about subdiffusion, which you can see as a blue line in the graphic on the right-hand side. If alpha is equal to 1, we speak about normal diffusion, which is the green line. And if alpha is bigger than 1, we are speaking about superdiffusion, which is the red line in the figure. So now there are several possibilities to realize such potential law for the variance. The first part is we substitute the usual time derivative by a fractional time derivative. We are arriving at such kind of equation where we have to add the initial problem, the initial value for our distribution function. This capital derivative, d alpha over dt alpha, is the so-called Caputo differential, which is defined by an integral with some parameters before from h to t. In this definition, we can find some special cases. So if h goes to 0, then we have got so-called Riemann calculus, and if h runs to minus infinity, we have got the so-called Liouville calculus. The second possibility is that fractional space derivatives can be replaced by the so-called Riesz operator, which you can find in the second line of the slides, by a more complicated integral. A closer look shows that the case beta equal to 2 must be omitted due to the fact that in this case we are getting a pole. That means that our diffusion equation can be reduced to this one which we can see next. The third possibility is that we can substitute both derivatives, the derivative in time and the derivative in space, by the special fractional differential derivatives. This kind of equation can be applied, for example, for charge carrier transport in amorphous semiconductors, the diffusion of chemicals in subsurfaces, aquifers. We can find such equations in chemical reactions and in single diffusion. So now let us have a look in the structure of the solution and how to apply the momentum. That means we are starting with a problem which one can find in the paper of Schneider and Wies. They started from a usual diffusion equation, and then they integrated this diffusion equation by time. The usual time integral then is substituted by the Riemann operator, by the Riemann integral operator. And that means we have to solve the equation which you can see on the right-hand side. The fundamental solution of this equation is that one with Fox H function, which you can find one line below. The Fox H function is defined by the Melling transformation, and it gives a product of several gamma functions, as you can find below. For the momenta in infinite boundaries, we integrated from minus infinity to plus infinity, we will find the equation in the last line before, which gives then for the norm n equal to 1, the expectation value is 0, the variance is proportional to t to the power alpha, and the asymmetry is also 0. If we consider the second problem, where both derivatives are substituted, we have got the equation in this form you can see on the next slide. The fundamental solution gives also, again, Fox H function, and in this case, the momenta with infinite boundaries, the expression is a little bit more complicated. And in order to understand this, we have to take into our consideration two cases. In the first case, beta runs from 0 to 2, and this gives us the zeroth moment is 1, the first moment is 0, the second momentum is also 0, and the third momentum is also 0, which means that the momenta which we are considering, expectation value, variance, and asymmetry, are always 0. The second case which we have to take into our consideration is the case beta runs to 2. This means that the zeroth moment vanishes, the first moment vanishes, the second moment is proportional to t to the power alpha, and the third moment is also 0, which means that our momenta, which we are considering, don't exist, especially for the variance. So these examples show that we have to take into our consideration finite boundaries in order to reduce the space to usual one and to get relevant results. So if we now want to compare our this theory with experiments, we have got the following situation. We are investigating an initial value problem, which means we are looking at our heat conduction equation and we have got our initial values. This initial values in our case is the temperature distribution at the time t0 along the x-axis. So the special solution for this is a Fourier convolution with the fundamental solution. That means we can represent it by an integral from alpha to beta from the product of the fundamental solution and the initial values problem. Then the general solution of all is then by linear superposition the sum of fundamental solution and the solution of our initial value problem. So if we use this solution structure now and taking the variance of it, then we see we have the variance on the left-hand side, and we have to take the variance of a sum, which means the sum of the variances. And if we make some calculations, we will arrive at an equation, where on the left-hand side we have quantities which we can determine by measurements, and on the right-hand side we have quantities which can be determined by theoretical figures. So this theory now we can apply to an experiment, so-called Poznaniak experiment. That means we are taking an aluminum rod of 45 centimeters and 4 centimeters in the diameter. One end is placed in a cold thermal reservoir of a double-walled cylindrical vessel, and there is a water flow of temperature 290 Kelvin between the wall and the vessel. The other end is placed on a hot thermal reservoir at temperature TH, which is generated by an electric heater. The number 1 till 6 marks the position at which the temperature is measured. There are thermocouple fixed, and the lateral surface of this rod is thermally isolated. So with these thermocouples, we can get the heating curves. We can measure the time, the temperature at each time, at each position. And what you can see here is the temperature difference, measured temperature minus the constant temperature at the end, as a function of position x and t. The numbers at the side, at the right-hand side of this figure, indicated the distance of the 6 thermocouples from the hot thermal reservoir. The next point is, if we want to determine the general momentum, we have to multiply this distance from the thermal reservoir with the temperature at this position, and after that we have to take summation over all. And also we have to run through all distances where the thermocouples are located. So this means if we are first dealing with the variance in infinite boundaries, we remember our definition of the variance. We have our fundamental solution. We can determine the momenta in infinite boundaries, which gives this expression with gamma function. And if we take m equal to 2, then this expression reduced to that what we know, that the variance is proportional to the first power of t. In the right graphic, we see the line, which represents the so-called Einstein variance, and the related scale is on the right-hand side. The green dots are the variance from the experimental data, and the related scale you can see on the left-hand side. That means we have significant deviation of Einstein variance and the measured variance. So if we are considering now the momenta in finite boundaries, we have got our Cauchy problem, which consists of heat equation plus Dirac delta function as initial condition. We have our fundamental solution, and we can calculate the momenta in finite boundaries by taking the integral from alpha to beta, first place of the thermocouples to the last place of the thermocouples, x to the power m, and the fundamental solution, which gives difference of gamma function multiplied by a factor. So if we apply this and compare theoretical and measurements, we first get an analytical expression for the expectation value, which is a quotient of difference of exponential function through a difference of incomplete gamma functions. The red dots are the experimental values of the expectation values, and by substituting alpha by 4 centimeters, beta by 24 centimeters, and using the interval halvening procedure, we will find our thermal diffusion of 0.98 multiplied by 10 to the power minus 6 square meters per second. If we are using this for the variance, the expression is a little bit complicated, but in the time of computer algebra, it's also not a problem. Doing the same as I described before, we will find an expression for A, which is in the which gives 0.8 multiplied by 10 to the power 6 square meters per second. And at least the asymmetry, this expression is again a little bit more complicated. and applying the same procedure, we will find an A of 0.9 multiplied by 10 to the power minus 6 square meters per second. So we can conclude the following. First, we have the experimental data set of the Poznaniak experiment evaluated. From the calculation of the three momenta, we found the following values. From the expectation value, we have for A 0.98. From the variance, we have A equal to 0.80, and from asymmetry, we have A equal to 0.90, altogether multiplied by the power 10 to the power minus 6 square meters per second. The technical value from literature for our thermal diffusivity is about 0.982 multiplied by 10 to the power minus 6 square meters per second. The values show a good agreement to the technical value. But this example shows also a clear deviation from the linear profile of the variance. And that means that instead of modifying the diffusion equation by introducing a fractional derivative, we can also think about to use the momenta of the fundamental solution in finite boundaries and use these things to determine the quantity R. So the next steps in our investigation is the application of this method to other materials and to substances which with reported deviations from the linear profiles. So that is all. Many thanks for your attention, and please feel free to ask questions.